Last time we talked about adding and subtracting radicals, and today we're going to talk about the other operations, multiplying and dividing. And so let's start with multiplying. To multiply radicals, you actually just multiply the radicands, the numbers inside the radicals, together. 5x to the third times 10x is 50x to the fourth. But then you have to simplify. 50 is the same as 25 times 2. Our perfect squares come outside of the radical, and we're left with 5x squared root 2. The same process works for cube roots. 3 times 18 is 54. A to the fourth times a is a to the fifth. B squared times b to the fifth is b to the seventh. This is a cube root, so I'm going to look for perfect cubes. 54 is 27 times 2. I write a to the fifth as a to the third times a squared, and b to the seventh as b to the sixth times b. I take the cube root of my perfect cubes. I have a 3ab squared outside of the radical, and everything that I didn't circle stays inside the radical. Now the distributive property applies to radicals as well. If I want to multiply 2 root 3 by this difference, I'm going to have to distribute it to both terms. 2 root 3 times root 3. I can multiply those radicals together, and I get root 9. 3 times 3 is 9. Now 9 is a perfect square, so I can go further with this. Root 9 is 3, and I'm left with 2 times 3, which is 6. For the other term, I multiply the 2 and the 4 together. That gives me 8. And then root 3 times root 6 is root 18. 18 is not a perfect square, but it can be simplified. 18 is 9 times 2, and root 9 is 3. 8 times 3 is 24. So I'm left with 6 minus 24 root 2. We can't go any further with this because those aren't like terms. They're not like radicals. Here's another multiplication problem. In this problem, I'm multiplying two radical expressions that each have 2 terms in them. This looks like a FOIL problem, and it is one. We can use that acronym FOIL to help us remember to distribute every possible combination of terms. The first two, root 3 times root 3, is root 9, or 3. The outer two, root 3 times negative 5 root 5, is negative 5 root 15. The inner two terms, 2 root 5 times root 3, becomes 2 root 15. And finally, the last two terms, 2 root 5 times minus 5 root 5 is minus 10 root 25, but 25 is a perfect square, and that becomes 10 times 5, or negative 50. Notice when you're taking root 5 times root 5, you're squaring it, and that's why you just get 5 without the radical. Finally, I'm going to combine like terms. 3 and the minus 50 give me minus 47, and then the outers and the inners are like radicals. 5 minus 2 is minus 3, so minus 3 root 15. My next example also looks like a FOIL problem, and you can definitely do this problem with FOIL. However, in this special case, these expressions fit into a pattern. We are actually multiplying conjugates together. In other words, the radicals are the exact same. The thing that's different is the sign in between them. We have something of the form a plus b times a minus b. This is our difference of squares formula. If we FOIL this out, we should get a squared minus b squared. In this particular case, the a would be root 7, and the b would be 2 root 5. Root 7 squared minus 2 root 5 squared becomes 7 minus, 2 squared is 4, root 5 squared is 5, so you end up with 7 minus 20, or negative 13. Notice when you multiply conjugates together, you end up getting a rational number, a number that doesn't have any square roots in it. Now, if you would prefer to use the FOIL process on this problem, it is not wrong at all. That is perfectly fine. I show you this method because sometimes it's a little bit faster. Now to multiply root 5 plus 2 squared, I would use FOIL on this problem. This means we're taking root 5 plus 2 and multiplying it by itself. First two, root 5 times root 5 is 5. Outer two, root 5 times 2, there's nothing we can really do with that. I'm just going to write it as 2 root 5. My inner 2 is the exact same thing, 2 times root 5. And my last is 4. Finally, I'm going to add these numbers together, combining like terms, and I'm left with 9 plus 4 root 5. Note, when you're squaring a sum or a difference, you can't just distribute the exponent. I think it's best to use the FOIL process on these problems. If you would prefer to use a formula, I have the formula written down below, but I'm not even going to bother showing you the problem with this formula because I think for most people it's easier to just use that FOIL process. Finally, let's do some division problems. If we want to divide two radicals, we can divide as we normally would, and then simplify. 60 divided by 2 is 30, a to the 5th divided by a is a to the 4th, and b divided by b to the 7th gives me a b to the 6th in the denominator. Now I'm going to try to simplify. I'm going to look for perfect squares. 30 is not divisible by 4, or 9, or 16, or 25, but a to the 4th and b to the 6th are perfect squares. Those are going to come outside of the radical. Notice when I pull my perfect squares out, if something was in the denominator, it stays in the denominator. So the b to the 3rd, which is the square root of b to the 6th, is in the denominator. Everything else is in the numerator. We can do the exact same thing with cube roots. We're going to do the division first, and then we're going to try to simplify. 80 divided by 5 is 16. A to the 7th divided by a squared is a to the 5th. And if we cancel a b out, we're left with a b to the 3rd on the bottom. I'm going to look for my perfect cube factors, and I know that 16 is 8 times 2. I'll factor a to the 5th as a to the 3rd times a squared, and b to the 3rd is already a perfect cube. My perfect cubes come outside of the radical. Again, anything that was in the denominator stays in the denominator. That's why I have that b in the denominator. Things that aren't perfect cubes stay inside the radical. Now, in each of my previous division problems, I didn't end up having radicals or square roots in the denominator, and that was kind of nice. In fact, it's considered bad form to have a radical or a square root in your denominator. And so part of our simplification procedure, when we have division, is going to be to do something called rationalizing the denominator. This just means get rid of square roots in the denominator. If you have something with just one square root in the denominator, like 1 over root 3, you can rationalize it by multiplying the top and bottom by whatever that denominator is. 1 times root 3 is root 3, and root 3 times root 3. So rationalize, this is root 3 divided by 3. I can use the same process on a fraction, like square root of 3/5. If we think of this as root 3 over root 5, I think it's a little easier to see what to do. We're going to do the same thing we did before. We're going to multiply by whatever is in the denominator. Root 3 times root 5 is root 15, and root 5 times itself is just 5. Now, this technique of just multiplying by the radical you see in the denominator only works if the denominator has one term. As soon as you see a sum or a difference, like I have here, in that denominator, you're going to have to do something a little bit different. What we're going to do to rationalize the denominator is actually multiply by the conjugate, which basically just means we change the sign. We have a root 3 minus 2 in the denominator, so we're going to multiply both numerator and denominator by root 3 plus 2. I have to distribute in the numerator. Root 2 times root 3 is root 6. Root 2 times 2 is 2 root 2. I'm going to use my difference of squares formula in the denominator. Root 3 squared is 3. 2 squared is 4. 3 minus 4 is negative 1. And root 6 plus 2 root 2 divided by negative 1. Oops, I have a mistake in there. There we go. Root 6 plus 2 root 2 divided by negative 1 is negative root 6 minus 2 root 2. Alright, that's it for our operations on radicals. Let me know if you have any questions.